So I'm going to go over line integrals in section, I believe, 16.2. And I want to start by going over a regular definite integral of a function that you guys did learn in Calculus 1. The definite integral of a function is done over some interval of x. So say we have some function y equal to f of x in 2 dimensions and some interval a to b. And what we did was that we took the interval a to b, we partitioned the interval into n partitions. So here you have, again, x0, x1, x2, all the way to x sub n. And let's say this is one of the intervals. We call this x sub k minus 1, x sub k. This is, as you know, the kth interval. And we take some point in that interval. That point is x sub k star. Okay, so what we did was that we drew the height starting from the x-axis to the function. Okay, and then we use that as the height for this kth rectangle over that subinterval. So here's that kth rectangle, and the area of that kth rectangle was f of x sub k star. X sub k star, again, is just a point in that kth interval. This is the height of that of the kth, or of that sample point. Okay, and then we took that and we multiplied by the width of the interval, which is delta x sub k. Okay, so delta x is the width, and it is obtained by basically subtracting those. Okay, so f of x star k times delta x sub k gives you again the area of that kth rectangle. Okay, so this is done for all intervals. You draw rectangles over each interval and you add them up, k or I, whatever you want to call the index, it doesn't really matter. So k from 1 to n gives you the total of those areas. And when you take the limit of this sum, the limit of the Riemann sum, you get the total area under the graph, which is defined as the definite integral from a to b of f of x dx. Okay, the limit of the Riemann sum is the definite integral of f of x over a to b. Okay, so, well, what does this have to do with line integrals? A line integral is a new kind of integral, and it has to do with a function of 2 or more variables. So we have let's say we have a function of 2 variables, z equal to f of xy, and that is a surface, right? It's a surface. So how can you do the integral of a surface? We are not talking about a double integral or a triple integral, okay? So let me tell you what the idea is all about. Okay, so what we do is instead of taking the interval a to b and breaking it into sub-intervals, we take a curve. So this is some curve. It is a parametric curve. Okay, so C here is given by x equal to x of t, y equal to y of t. This curve could also be in 3 dimensions, but let's just say we have this curve in 2 dimensions. And what we do is we break this curve into sub-curves. Okay, so the initial point is, it corresponds to t equal to a. The final point corresponds to t equal to b. These are points that you obtain by plugging t into the parametric equations. All right, so again, we break this curve into sub-curves. As we did break the interval a to b into n partitions, we partition this into n sub-arcs. Okay, so for example, that would be T1, T2, T3, and so on. Now notice that here we don't have a delta x anymore. Okay, we have a delta s. Remember S is the arc length. Okay, so the length of each of these sub-curves is an increment of arc length. So this would be delta S1, delta S2, and so on. All right, and also consider a sample point inside inside one of the intervals. We'll call that x sub k, y sub k, again star. I actually do have a better picture that I'm going to show you here. All right, so this is our curve into dimensions that we broke into n sub-arcs. And this is the p sub 0. We call that point p sub 0 corresponding to time a, p1, p2, and so on. And again, this is the kth sub-arc or sub-curve or whatever you want to call it with a sample point in there. And as I said, the length of each of these sub-arcs is a delta s, not a delta x, not a delta y, but a delta s. Delta s is the arc length increment. If you remember delta s from previous sections, I think this was from chapter 13, you can get delta s ds by using the Pythagorean theorem. We do dx squared plus dy squared, if you remember. Okay, and if it's so that's ds squared, okay? Yeah, so this is just arc length from chapter 13. So what do we do with this curve, this parametric curve? Now we have a function of x and y right here, as you can see, whose graph is a surface. And we have this curve, the one that I drew here, in the xy plane. Okay, and the goal is to integrate this function over this curve. And that is called the line integral of f. Okay, so again, here we integrated this function over the interval AB, but for line integrals, we integrate the surface, the function, over a curve that is in the xy plane. So what does that really give us? If you think about it, it is going to give you the area of, so for a second, imagine the projection of this curve onto the surface, okay? What we get is geometrically the area of this basically curtain-like surface that suspends from the surface of X and Y. All right. Yeah. So assume that our curve here is, again, parametric. All right. So here we have a parametric curve and it is smooth. So the way the line integral works is that we take a sample point from the kth interval. All right. We have a sample point actually in each interval, in each sub-arc, and we plug it into the function f of xy. So we get f of x star y star, okay, which gives you the distance from the xy plane to the surface. That's basically the z corresponding to the point x star y star. Okay, and I have that right here. You multiply that by delta s. Okay, so right there, what happens is that you're going to get the area of the kth rectangle. So in this picture, that kth rectangle would be this rectangle over here. Okay, again, we took z, we multiplied by delta s. All right, and then you add them up just like a typical Riemann sum, and then you take the limit of the Riemann sum as n goes to infinity. So comparing this to a regular definite integral, okay, we have f, we are plugging x star y star into f. This is analogous to f of x star. Delta s is analogous to delta x. And then we have the sum of that, then limit as n goes to infinity. This is defined as the integral. This is, guys, this is a single integral, right? It's not a double, again, not a double integral or a triple integral of the function xy, and the integral is with respect to s. It is with respect to arc length. So again, we have a single integral because we are simply adding up these areas, okay? And again, that's just z, right? Z times delta s, length times width, okay? So again, we call this the line integral of f of xy along the curve C with respect to arc length, right? So again, the integral of f over C with respect to arc length. Now, this integral is extremely simple to evaluate. Let's see how the setup is done. So if you have a line integral of a function with respect to arc length, what happens is that the x and y of the function are going to be replaced with the parametric x and y. And that's because you're looking at the trace of the curve on the surface. Okay, so you put the x of the curve into the function and the y of the curve into the function. And again, ds is the arc length increment from, I think, section 13.3 or 13.4, which is defined by the root of dx dt squared plus dy dt squared. Remember, this is also the magnitude of r prime, remember? Yeah. And the idea also extends into higher dimensions. The line integral of a function of 3 variables, this no longer is a surface, is again the function at the x, y, z of the curve, and ds is the arc length increment in 3D. Okay, so here is the R notation for line integral. So let's say C here is given by a vector value function, x of t, y of t, z of t. This is again the vector value function of a curve in space. And let's say that this curve begins at t equal to a and goes to t equal to b. Okay, and we want it to be smooth, of course, because we are finding r prime. Okay, if the curve is not smooth, then r prime will be problematic. If c is not smooth, you won't be able to find the arc length increment. It could be undefined. Okay, so again, the line integral of f, okay, on c with respect to arc length is equal to the integral t goes from a to b. And what we are doing, as you saw over here, we are plugging, see, that's r of t. We are plugging r of t into the function. That can be seen down here, f of r of t. Okay, and once again, this thing here is just the magnitude of r prime, right? That's r prime magnitude dt. So let's do an example. Here, our first example, we are finding the line integral along C of the function as x, y squared with respect to arc length. And then here C is given by x equal to cosine of t, y equal to the sine of t, where t goes from 0 to pi over 2. And you do know that this is the parametrization for a circle of radius 1, because there's just 1 in front of sine and cosine. And when t goes from 0 to pi over 2, the arc is just a quarter of a circle. Okay, it goes from this point to this point, right? 0 to pi over 2. If it was 0 to pi, we would get half a circle. And guys, orientation here does matter a lot. When we are doing line integrals, orientation is going to make a huge difference. One thing I should point out, guys, is that we have this function that is over it is casting, let's say, a shadow over the xy plane, right? And you don't need to draw this function. We don't need the drawing. We don't care about it. We just need the part of the curve that we are integrating the function over, okay? We are integrating xy squared over this curve. So the name should really be curve integral instead of a line integral. It could be a little confusing. This is, as we know, this is not really a line. Okay, it is a curve. We are doing the integral of the function over the curve. So if you want to call it a curve integral, be my guest. So what do we need for the integral? We need dx dt. We need dy dt. Take those derivatives. And what you want to do is you want to calculate the arc length increment. That would be ds. Let me actually write that over here. ds. Okay, well, this is not ds. It doesn't have the dt, but calculate the square root. This is the magnitude of r prime, as you know, which gives you just 1. Okay, so here the magnitude is 1. So now you're going to rewrite the integral in terms of t. Okay, yeah, so the line integral along this curve is going to be the integral from 0 to pi over 2, because again, this curve runs from the point corresponding to t of 0 to the point corresponding to t of pi over 2. So from 0 to pi over 2, and then x is replaced by cosine of t. This is y squared. Y is replaced by sine of t, so you get sine squared t. And then we need ds. ds is the square root of dx dt squared plus dy dt squared, which is just 1 dt. So the integral turns into a simple, hopefully simple trigonometric integral, which can be done by a u substitution, right, guys? If you let u equal to sine of t, then du is just cosine of t dt. We do have cosine t dt here, and we could change these limits. Plug 0 for t, sine of 0 is 0. Pi over 2 goes for t, sine of pi over 2 is 1. And that integral is going to be 1/3 u cubed from 0 to 1, which is equal to 1/3. So what is the meaning of this line integral? This is just a line integral. But if you want to give it a geometric interpretation, then you can use the curtain argument, right? Or the fence argument. So imagine we have a surface right above the xy plane. If you were to run a fence or a curtain from the surface to this curve, as we see in this picture, so the curves has a projection on the surface, draw these fences from the ceiling to the floor, the area of this curtain will be 1/3. That's what it means. Okay, so is that something we really care about in real life? No. These integrals have other applications that we're going to learn about in a little bit. Okay, so Yes, here we have I have another example. This is the integral along a curve. This is now, guys, a space curve, which actually happens to be a line for this example. And the function is a function with 3 independent variables, x, y, z. So this is no longer a surface. This is just a 4th dimensional function. And again, the integral is done with respect to arc length. They say that C is a line segment from 0, 0, 0 to 1, 2, 3. It is just a line segment. So you could truly call this a line integral from 0, 0, 0 to 1, 2, 3. Now, what you need to do, since they didn't give you the parametric equations of this line, your job is to make it, to come up with those parametric equations. And this is exactly why we learn about parametrization of a line in chapter 12. Remember, if you want to find the segment, the line segment from one point to another point, okay, first of all, you need to come up with the vector. The vector that is parallel to the line. And that vector, the parallel vector, is obtained by finding the vector from the initial to the final point. Guys, orientation, direction here matters 100%. You can't ignore that. I can't just come up with a vector parallel to PQ. It has to be the vector PQ from P to Q, not from Q to P. Okay, so find that vector PQ by just doing components of Q minus the components of P. It's just the vector 1, 2, 3. Okay, so our parametrization, remember from chapter 12, you take the initial points. You take the initial points and you add the component of the parallel vector times t. Always. You should have this in your chapter 13 notes. So 0 plus 1 minus 0 is really that 1 times t. Then we have the second coordinate of the initial point is 0 plus 2 minus 0 is again is the j hat component of the parallel vector. And z likewise 0 plus the k hat component of the parallel vector times t. And t always runs from 0 to 1. That's how this parametrization is done. T is from 0 to 1. And if you want, you can write this in vector value function form to make you to do less writing. So R of t represents the line or the curve that you're integrating over. This is what we just found. 1t, 2t, 3t, t goes from 0 to 1. You can check to see if this parametrization works. It's supposed to connect these 2 points, and it does. If you put 0 for t, you get 0, 0, 0. It gives you the position of the initial point. And if you put 1 for t, you get the vector 1, 2, 3, which gives you the position for the second point. Okay, so again, it's got to be in that exact order. All right. So let me see if I could do some drawing here for you. In terms, you don't have to draw the curve or the line in this case either, but but here it goes anyway. So we have the x, y, z, and this is P. This is the initial point. The final point, 1, 2, 3, we go 1 on X, 2 on Y, and then 3 on Z. So somewhere around here is Q. All right, so C is the segment. It's that line segment. And again, we want to integrate. We want to find the integral of this 4-dimensional function over this line. What does that mean? Absolutely nothing. It means nothing. Geometrically, it doesn't mean anything. All right, so what do we do next? Once you have your RFT, if you don't have your RFT on your own, you have to find it. You do find it. Next, you want to find the arc length increment. That's ds. Okay, and ds, if you recall, it is the magnitude of r prime times dt. Okay, so what you need to do next is to take the derivative of r. The derivative of r is r prime, which is the vector 1, 2, 3. All right, so this is your dx dt, dy dt, and dz dt. Yeah, so I had to pause the video and go quiet my little boy. But yeah, I was saying that if you look at the integral, where are we? So again, we need the curve, the parameterization for the curve that you can write as a vector value function. We need the square root of the square of the derivatives added. That's also the magnitude of r prime. Okay, so again, we find r, we find the derivative of r, and we find the magnitude of that derivative, which in this case is just root 14, and that's a constant. All right, so the line integral of f of x, y, this is really f of x, y, z. Let me just quickly make that correction here. F of x, y, z for this function. It's a function with extra variable, but again, the idea is the same. Yeah, ds is when you take the function f, okay? We are looking at the function over this curve, over the line. So we plug again the curve, the equation, the parameterization of the curve into the function, and ds again is the magnitude of r prime dt. So let's do it. X becomes t. You write t for x. And then we have e to the power of y is going to get replaced by the y of the parameterization. That's 2t. And z is going to get replaced by 3t. Right there. And ds is square root of 14 dt. And look at that. This just turns into the integral, a single integral of just t. Square root of 14 is a constant factor. Take it out. You have the integral from 0 to 1. And that's because this parameterization is from 0 to 1. Right? Someone else might do the parameterization differently. They could come up with a line where t goes from 0 to 2, but again, this is the standard way of doing the parametrization of t e to the power of 2 times 3, that's a 6. E times t is a t squared. So again, an integral in terms of t only. And for this integral, we just do a simple u substitution, right? U is 6t squared. Du is 12t dt. You divide by 12, 1/12 du is just t dt. So this t dt is going to get replaced by 1/12 du. And the 1/12 is, again, it's a constant factor that you can kick out of the integral. Okay, so t, again, it's gone. That's just the 1/12 du. You have e to the power of 6t squared is just u. Changing the limits, you put 0 into t, you get 0. Right, 0 goes into t squared, you get 0. And 1 goes into t, you get 6. That's the upper limit of integration. The antiderivative of e to the u is e to the u. With the root 14 over 12 out, just plug in 6 and 0. So you get e to the 6 minus e to the 0, but e to the 0 is 1. And that is the value of the line integral. Okay. So again, we're going to understand why line integrals are needed. All right, now we can modify the line integral a little bit here. Okay, so we've been looking at the line integral with respect to arc length. So there, line integrals with respect to arc length. This is a ds. You are partitioning the arc length. We can likewise do a line integral with respect to x, or with respect to y, or with respect to z. Meaning that instead of having a ds, we could have a dx. That would be the line integral of f along c with respect to x, or with respect to y, or with respect to z. So since, again, just like before, the line integral is done with respect to, or it's done with the over c, since the line integral is done over c, then you're going to replace x, y, z with the equations for c. X of t, y of t, z of t. You plug in the curve. Plug the curve into the function. Dx is going to be x prime dt. So for example, if x is t squared, dx would be 2t dt. That would kind of replace ds. In this case, dx, x prime of t dt. If you look at the original formula, guys, right there, if you look at the original formula, you could just get rid of dy dt. When you do that, you get the square root of dx dt squared. So that goes away because it's going to cancel dt, and you just get dx alone. I hope that wasn't confusing. But dx is just x prime of t dt. If the line integral is done with respect to y, then here you have y prime dt. Likewise, you could have a line integral of f along c with respect to z, dz. That becomes z prime dt. Okay, so let's look at this new line integral. These line integrals are actually easier because you're not calculating a ds. But we have the integral of x squared y plus sine x along C with respect to y. And they give you C, so C here happens to be the arc of y equal to x squared from 0, 0 to pi squared. Let me see if I can draw that for you over here. So 0, 0 is right there, and we have pi, let's say here, pi squared here. So y equal to x squared is just a parabola. We want to integrate the function along this parabola. Okay, in this direction, they say from here to here. Okay, so we begin by coming up with a parametrization of C. They did not parametrize C for you, but you can easily parametrize a given curve. Okay, by letting x be t, and obviously y is t squared because this says y is x squared. If you chose x to be t, then y is t squared, right? So yeah, and then we could let t go from 0 to pi, and that's what's happening here. T goes from 0 to pi because our x goes from 0 to pi, so that's t, since t is equal to x. So this line integral turns into the integral of replace x with t. X becomes t, so we have x squared, t squared. Then y is t squared. Let me fix that. This y is a t squared. So we put t squared for this y. Therefore, there should be a square over here. Plus the sine of x, and x here is just t. dy is the derivative of y. Since y is t squared, the derivative is 2t. So dy becomes 2t dt. All right. Yeah, we have this 2 that we can take out. Here is the 2 factored out. The integral goes from 0 to pi. That's the range of t, as you see. And then this is the integrand. So integrate that. The antiderivative of t to the 4 is 1/5 t to the 5. Then we have the antiderivative of t sine t, which requires integration by parts. I showed you guys a shortcut in class. We have 2 parts, t and sine t. Okay, put t here, sine t here for the shortcut table. Take the derivatives of t. The derivatives of t, 1, 0, stop. Once you get 0, you stop. Then for the other part, the sine t part, you find antiderivatives. Antiderivative of sine t is negative cosine t. The antiderivative of negative cosine t is negative sine t. Then you're going to multiply, right? Multiply that by that. That's integration by parts, t negative cosine t. And then you alternate the sign. Okay, so first one, you don't change the sign. Second one, you change the sign. You do 1 minus negative sine t. And that gives you positive sine of t. t goes from 0 to pi. And that is the integral. All right. So finally, we are going to have to, for valid reasons, to look at a combination of line integrals. This idea is very, very important. A combination of line integrals. Well, what is that? Imagine we have line integral with respect to x and with respect to y, or with respect to z. A combination of these is what we want to find. Imagine these three integrals are added. That's called a combination of line integrals. Okay. Here I have two functions that are functions of x and y. Here you have a p of xy. P of xy is just like f of xy. This is the line integral of p with respect to x, not s, just x, y, or z. And we are adding to that the line integral of a different function, not the same function, different function over c with respect to y. In short, you can write this as a single integral along c, because these are both along the same curve, of, without parentheses, no parentheses, p dx plus q dy, right? So p dx plus q dy, and the integral of that. Okay, in three dimensions, you could have an extra function. Extra function, let's say, is r, and we could do the line integral of that with respect to, let's say, z. So this is the line integral of p dx plus q dy plus r dz. You're finding all three line integrals simultaneously. And this is all just a matter of taking the given c, the given curve, whose parameterization is given, right? Plugging that into the functions and multiplying it by the proper derivative. Let's look at this example. Here we have the line integral along c of y dx. So here p is the p function is just y, plus z dy, that's the q function, plus x dz. Here r is just x. It could be something more complex for these, but this is the line integral. It's done along c, where c is given parametrically by x equal to square root t, y equal to t, and z equal to t squared. Okay, so what you want to do first is to find the derivatives. Okay, you want to find dx, dy, dz. Dx is x prime dt. Find x prime. X prime is simply the derivative of x. Y prime is the derivative of y. The derivative of t is 1. And since z is t squared, z prime is 2t. All right. Yeah, now we are ready to plug in to find the line integral. This becomes the integral from 1 to 4, because they tell you over here that this curve should be considered from 1 to 4 for t. This is given. Okay, of y is replaced by whatever y is defined as. so t. Okay, then dx is x prime. That's 1 over root 2t. Plug that in, and then you have dt plus z is t squared. Plug that for z, and then dy is 1 dt plus, then we have x. X is defined as root t. There's your x, it's root t. And then dz, you found dz, that's the derivative of z. That's 2t. dz is 2t dt. Right, so all the terms are in terms of t. Okay, you can factor dt out right there. Multiply or simplify these. T over 2 root t is just 1/2 root t. Here just half t squared. And here we have root t times 2t. That's 2t to the 3/2. Root t is the same as t to the 1/2. When you multiply by t squared by t, you get t to the 3/2. So this is really an integral from now calculus 1. All right, find the antiderivatives. The antiderivative of root t is t to the 3/2. The antiderivative of t squared is 1/3 t to the 3/2. And the antiderivative of t to the 3/2 is t to the 5/2. Then, but then you multiply by 2/5. I gotta multiply by 2/5. That 2 times 2/5 is 4/5. Going from 1 to 4, just plug in. And again, we're not so concerned with the ultimate value, but that's how that line integral is done. We're almost done. Just need one more thing to mention here, and that is the line integral of a vector field. Okay, the line integral of a vector field. If you look at this line integral, so we have the line integral of p with respect to x, q with respect to y, and r with respect to z. And again, these are just functions, as we saw over here. Notice that this is a dot product. P times dx plus q times dy plus r times dz. This is a dot product, right? It's a dot product of p, q, r and dx, dy, dz. So let's look at the new page. Yeah, so let's say we have a curve that we are integrating over, r of t, given by this vector value function. dr dt, guys, is just the derivative vector. That's also known as the velocity vector or the tangent vector. Okay, then you could say that dr, if you want to get dr, just multiply this by dt, right? Multiply by dt, the dt's cancel out. dr is just dy, dx, dz vector. All right. So notice that this line integral, the combination of line integrals over c that we were looking at is the dot product of the vector PQR. This is a vector field. right? These are functions. We have P of X, Y, Z, Q of X, Y, Z, R of X, Y, Z. This is a vector field that we are dotting by dx, dy, dz vector, and that is what we call dr. Okay, so this becomes the line integral over curve of f. If you call this vector field f dot dr. So this is the new notation for a line integral. The line integral of the vector field f over c. Okay, and again, the way this is done is by taking the curve. We take the curve, we plug it into these functions. And this is just r prime of t dt, and there's a dot between those right there. Okay. Now, what is the importance of this line integral? This line integral is the calculation for work. Okay, so this line integral calculates the work done by the vector field F. Imagine F is the force field. At every point in space, there is a vector that tells you the force at that point. Okay, so this line integral is the work done by the force or the vector field to move a particle along C from the initial to the final point. Okay, so imagine we have a curve, and this curve is in space, right? There are vectors here. What do these vectors do? What do these vectors do? They push and pull things around. They move things around. So what this vector field does is that it moves a particle along this curve from one point to another point. Okay, we want to know how much work was done by that vector field for this movement. Okay, so work is the line integral of the vector field. Yeah. All right, so let's do a problem. Yeah, so just imagine, again, this goes back to chapter, I believe, 12, that if you look at work is force dotted with displacement. And this dr is the displacement along the curve from one point to another point on the curve. I've done the proof here, you can look at it. But a question here is to find the work done. This is a fairly long question, but we just get through it. Find the work done by this vector field. So this has a P component, that's P of X, Y, Z. This is Q of X, Y, Z. And this is R of X, Y, Z. To move a particle from the origin, okay, to the point 101. Let me see, I have done some drawing here for you. So here's the origin. We want to go from the origin to the point 101. Okay, then from this location to a new location, which is 0, 1, 2. Right, so the path consists of two paths. C1 goes from the origin to this first stop, 101. And the second path is from 101 location to the new location of 012, right? Those lines, right? Those paths are linear paths. So your job is to parameterize, come up with the parameterization of each of these paths. Okay, and we hopefully already know how to do that parameterization. Okay, so you're going to have two line integrals, one line integral along C1, and one line integral along C2. Okay, so let's do the parameterizations. If you want to go from 0, 0, 0 to 1, 0, 1, okay? Yeah, we need, again, we need the line, which is given by the function R, I'll call that R1 of t. So remember again, we're gonna need the parallel vector. Okay, so what is the parallel vector? The parallel vector is the vector from the first point to the second point. How do you find that vector? You do the coordinates of the second point minus the coordinates of the first point. So we do 1 minus 0, that gives you 1. Then we do 0 minus 0, that's 0. And we do 1 minus 0, that's 1. Okay, and then the vector function is going to be always the coordinates of the initial point, right? So the coordinates of the initial point plus the components of the parallel vector times t. So 0 plus 1t gives you t. All right, 0 plus 0t, that's just 0. Oh, what right here? 0. And then we have 0 plus 1t, that's equal to t. Okay, so this path, and again, always t goes from 0 to 1. And this is the vector value function for this path. Okay. So while you're at it, you find the derivative. We find the derivative of R1, the vector 1, 0, 1. Take the derivative, you get 1, 0, 1, which actually happens to be the same as the parallel vector or the direction vector. Okay, for R2, we do the same thing. R2 is from the second point to the third point. Let me find the direction vector. Okay, so again, you take the coordinates of the second point minus the coordinates of the first point. So we do 0 minus 1. That'd be -1. Okay, we do 1 minus 0. That will be 1. And we do 2 minus 1. That's 1. This is the direction vector for the second path, C2. Okay, so now we are ready to come up with the vector function for C2. And again, you always take the initial point's coordinates plus the components of the direction vector times t. Okay, so let's do it. We have 1, 1 plus -1 times t. There you go, 1 minus t. That's the first component of the second R. Okay, the j hat component is going to be the y coordinate of the initial point, which is 0, plus the j hat component of the direction vector, which is 1, times t. And that just gives you t. There you go. That's the j hat component of the second R. And then finally, we have the z coordinate of the initial point. That's 1, plus the k hat component of the direction vector, which is 1, times t. So you get 1 plus t. And that goes for the last component of R2. Okay, and again, t always goes from 0 to 1. Okay, so we need also the derivative of the path, the tangent vector, r prime. Find the derivative of this vector, r2 prime, negative 1, 1. And again, notice that this is the same as the direction vector for that line. Okay, so now we are ready to calculate the line integral. Okay, it is a very simple process. The integrals are typically polynomial integrals. You just have to carefully substitute r into the vector field. Okay, so let's do the line integral along the first line, along C1. So what do? We are going to take carefully this r and plug it into the vector field, okay? Meaning that every x gets replaced with t. Every y gets replaced with 0, that's great. And every z will get replaced with t, x, y, z, okay? So yes, copy the vector field down with that replacement, right? So here it goes, here's that vector field. Y becomes 0, right there, plus z. Z becomes t, right there, 0 plus t, okay? Second component is x plus z. X gets replaced with t, and y gets replaced with, z gets replaced with t. So you have t plus t instead of x plus z. You could see that right here, okay? For the last component of the vector field, x gets replaced with t, y gets replaced with 0. So you get t plus 0 right there, okay? This is the vector field that we composed with the line, with the curve, with C1. And then you dot that with the derivative of the first r. The derivative of r1 is the vector 1, 0, 1. Do the dot product and, right, so do the dot product, you get t times 1, that's a t. This whole thing gets multiplied by 0, you get 0. T plus 0 gets multiplied with 1, so you just get t. So the integrand of the integral that should go from 0 to 1, because t goes from 0 to 1, is the integral from 0 to 1 of 2t, and the answer is 1. So what does this mean? This means that this vector field did a work. It did a work to take a particle from here to here along C1, and that work is just 1. 1 joule, 1 whatever unit of work. Okay, so now let's do the same exact thing for the second path. All right, so again, carefully, you're going to take R, plug it into the XYZ of the vector field, meaning that Y gets replaced with T, Z gets replaced with 1 plus T. So T plus 1 plus T, here is that replacement. So again, Y plus Z. Yeah, Y plus Z gets replaced with T plus 1 plus T. X gets replaced with 1 minus T. Z gets replaced with 1 plus T. So you get 1 minus T plus 1 plus T, which is right there. And in the vector field, last component, X gets replaced with 1 minus T. Y gets replaced with 1 plus T. So we get, again, Y gets replaced with T is what I meant to say. So here we get X plus Y, which is now 1 minus T plus T, okay? And then dr, we're gonna dot that with the derivative of the second r, which is negative 1, 1, 1. Okay, so that's dr2. All right, so do the dot product. You can begin by simplifying this vector field in terms of t. So here we have 2t plus 1 dotted with negative 1. You get negative 2t plus 1. For the j hat component, notice that these negative t's cancel out. We have 2. 2 times 1 is 2. And last component, t's cancel out. You just have a 1. 1 times 1 is 1. All right. Negative 2t. And then you have negative 1 plus 2 plus 1, which gives you 2. From 0 to 1. Integrate term by term. You get 1. All right. So the total of the two line integrals, you want to know how much work is done in total to go from the origin to the final point. Okay, going through these two paths is just going to be the sum of the two line integrals. Okay, C is C1 united with C2. That means you're just going to add the two line integrals. Each line integral gave you 1, just a coincidence that these are both 1. So the total of the line integrals is 2. All right, so that's the idea of line integrals. I do have extra handouts, guys, that I'm gonna post online. So this is a handout that I made for section 16.2 and 16.3. We haven't done 16.3 yet, but I'm gonna post these handouts on Canvas, and I want you guys to complete the handouts. I do also have the solution to these. The solutions are done with details for you that again you can look at. But yeah, I hope this lecture wasn't too boring, and I hope it was easy to understand. All right, so talk to you later.